Hello everyone and welcome to our video dealing with the limit review. This will cover sections 1.2 on numerical and graphical limits out of the textbook and section 1.3 evaluating limits analytically. The objectives for this particular video: number 1, estimate limits using a numerical or graphical approach. Number 2, learn different ways a limit can fail to exist. Number 3, evaluate limits using limit properties. Number 4, develop and use a strategy for finding limits. And number 5, evaluate limits using dividing out, rationalization, and the squeeze theorem. Let's start out by looking at an informal definition of a limit. And to get an idea what a limit is and to help us recall what a limit is from our discussion last year, we're going to look at this function here. F of x is equal to x cubed minus 27 over x minus 3. Now right away on this one, you should recognize that at x equals 3, this thing here is undefined because our denominator would be 0. So this function actually will not have a value in this spot, so because it will be undefined. But what we're going to be looking to see is, are the function values, as we keep moving closer and closer to 3, are the function values approaching a specific number? So what we have to do on this, I'm going to use numbers that are close to 3, and we're going to start from the left. I'm going to use the values 2.9, which is very close to 3, 2.99, which is even closer to 3, and then 2.999, which is closer still to 3. And what happens in this case, when I put 2.9 in for x up here, I will get 26.11. When I put 2.99 in for x, I will get 26.91. And when I put 2.999 in for x, I get 26.991. And you look at that, you can say, as we move in this direction here, our function values seem to be approaching something, a specific value. You can notice that because, yes, we had 26.11. Well, we only went up a small amount, and then we're still going up an even smaller amount here from this point forward. And if you were to use something even closer to 3, you'd still see going up, but even at a smaller rate. Now what we're going to do then is look at what happens when we take values bigger than 3. So we'll use 3.1. It's very close to 3, but we can move closer with 3.01 and 3.001. And when I use 3.1, I get 27.91. When I use 3.01, I get 27.09. And when I use 3.001, I will get 27.009. And so you can see, as I move in this direction here from the right, again, my values seem to be approaching something. And the value that we seem to be approaching is, in this case, 27. So I would say in this case that the limit as x approaches 3 of f of x, in this case, equals 27. Now let's really kind of think of this in terms of an informal definition of the limit. The limit as x approaches c of f of x is the one number f of x gets closer to as x gets closer to but not equal to c. Again, let me say this again. The limit as x approaches c of f of x is the one number f of x gets closer to as x gets closer to, but not equal to. That's another important part. But not equal to c. Okay? That's what we're going to be looking for when we're working with these limits. What's happening as we keep moving closer and closer to a particular value, but not necessarily equal to that value. Let's start by looking at graphical limits. In this graph, you're going to see a function that has a lot of different things happening in it. Okay, so we notice here at A, we have a hole, or what's also called a removable discontinuity. We have closed circles there. open circle here with a closed circle right below it. And here we have a step, what's called a step discontinuity. Okay. Now what happens when we're evaluating limits? You remember the limit is the one number that my function values are getting closer to as my x values get closer and closer to a number but not equal to that number. So in this case, if I want to find the limit on this, let's say this function here is y equals f of x. If I want the limit as x approaches a of f of x, what I'm going to do is I'm going to look as I get closer to a, as I move close to a from the left and from the right. So I'm just looking really close to a anyway. As I come from the left, I'm traveling right down here, and my function values are getting closer and closer to 2. In this case, as I approach a from the right, so I just need to be somewhat just off, slightly off of a. And as I keep getting closer and closer to a, my graph is continuing to go down. And again, my function values are getting closer to 2. So in this case, the limit of, as x approaches a, of f of x is equal to 2. Now let's take a look at the limit as x approaches b of f of x. Okay. Now in this case, what we have a closed socket. The function is defined right at b. So again, we're going to be looking as we move closer to b from the left and from the right. So we're looking at these x values. So if I come from the left, I'm traveling here along the curve, and as I move closer and closer to b, my function values here are getting closer to 4. As I come from the right, so I just have to be kind of close, just off of b from the right. I'm going to be traveling along this portion of the curve, and again, my function values are getting closer to 4, which also happens to be where the function value at b. So in this case, that would be 4. Notice the differences between these two. In this one right here, this function is not defined at a. We have a hole there. There's no function value at a, but the limit is still 2. It's what if we could close that hole off, it would be what a would be to close that, make that a nice smooth curve. But in this case, it's not defined at a, but the limit is 2. Here, the function is defined at b, and the function value at b is 4, and that does also happen to be the limit. And that's okay. That's good. Now let's look at what happens at c. Take the limit as x approaches c of f of x. Now in this situation, you're going to notice something. Now we have an open circle here, right here, at this point. But it's also, we know that when I put c into f, I'm going to get this value here, which happens to be 4. Okay, so what we're having, but what you have to remember here again, the limit is the one number we are approaching as x moves closer and closer to, in this case, c, but not equal to c. So when x is moving closer and closer to c, but not equal to c, we're going to approach from the left and from the right. When I come from the left, when we're taking values that are closer and closer to c, but not equal to it, our function values are here, and I keep getting closer and closer to the value of 6. When I come from the right, I'm moving along here, and again, I'm getting closer and closer to 6. So in this situation, that limit is equal to 6. The last one we're going to look at is the limit as x approaches d of f of x. Now in this situation, as we're moving closer and closer to d, again, we have to look at when we're coming from the left and from the right. In this situation, as I come from the left, my function values are coming closer and closer to here, and they're getting closer to 4. As I come from the right, we are getting closer and closer to 2. My function values are moving closer to 2. So remember on this, the limit is the one value that we're moving closer and closer to as x gets closer to but not equal to, in this case, d. Now on this particular one, since we're getting closer to 2 different numbers, we would say that this limit here, the limit as x approaches d of f of x, does not exist. Or D, N, E. That's an E. So that kind of gets us a look at one of the spots, one of the things that can happen when a limit doesn't exist. Here is looking at some pictures where a limit doesn't exist. We already have one, it's very similar to this, where we have this what's called a step discontinuity. And what's happening here, again, as we're approaching two different values as we come from the left. As we come from the left in this case, we're going to 5. As we come from the right, we're going to 6. As x gets closer to 4. So in this case, this limit does not exist at x equals 4. It does exist at other values. It makes perfect sense for me to talk about the limit as x approaches 1 or -2 because I have there's no issue on this curve here. And same with values that are bigger than 4. They will all have a limit. The only place where this one is not going to have a limit is at 4. So this one is what's called a step discontinuity. Continuity. The next one we have is a vertical asymptote. Vertical asymptote, in this case, this is not, the limit does not exist there because we exhibit what is called unbounded behavior. As we move closer and closer to 4, my function values are just shooting way up, and a very, very small change in x is going to cause a very big change in the y value, and this happens from the left and from the right. So in this case we have a vertical asymptote, and that one is also a place where the limit doesn't exist. The other thing that where we can see this occurring is in something that looks graphically will look like this. In this bottom one here. In this situation here, our curve is coming along here, it's traveling here, but as we move closer to 4, the values just keep going up and down, up and down, up and down. It has very fast oscillating behavior. And in that situation right there, the limit does not exist because we are not approaching a specific value. And there are a couple limits that we're going to see where you can see this. One would be something where you could just look at the limit, or look at f of x equal the cosine of 1 over x. If you graph that out and look at this, look at what happens as we're getting closer and closer to 0. As you move closer and closer to 0, you're going to see this oscillating behavior take hold. Now I hope at this point you kind of remember how we dealt with finding limits last year. So now let's look at some of the limit properties so we can start looking at these things analytically. The limit properties that we have, we're going to let b and c be real numbers. N is going to be a positive integer. F and g are functions such that the limit as x approaches c of f of x equals some number L, and the limit as x approaches c of g of x equals some number k. Now we have 3 basic limit properties that we can use to go and help evaluate limits. Number 1, the limit as x approaches c of b is equal to b. Remember, b is a real number. There's no x there, so the limit as x approaches 2 of 7 is just going to be 7. The limit as x approaches c of x is going to be c, and the limit as x approaches c of x to the n is c to the n. Now these properties right here allow us to do some things in terms of some very basic functions, allow us to kind of move into doing some substitutions to help us out find things into functions. These other properties assist us there as well, but you're going to notice in this case we have some different operations. In the first one, it's what's called the scalar multiple. We're multiplying a function by a real number b, so the limit as x approaches c of b times f of x is just going to be that number times L. When I take the limit as x approaches c of f of x plus or minus g of x, I'm going to get L plus or minus k, which again, remember L and k were the limit as x approaches c of f and g respectively. And number 3, the limit as x approaches 3 of f of x times g of x is going to be L times k. Number 4 is a little bit different because it's the limit as x approaches 3 of f of x divided by g of x. You'll still get L over k, but that's provided that k does not equal 0. If k was equal to 0, then this one here would not exist. It would be impossible to find that limit. And the last one we have is the limit as x approaches c of f of x to the n power is going to be L to the n. So let's take a look at how we can use these properties now to evaluate the limits of functions. Let's take a look at our first one. The limit as x approaches 2 of 3x squared minus 5x plus 7. Well, using our properties here, I know that the limit as x approaches 2 of x squared would be 2 squared. And I have another property with the scalar multiple which said that the limit as x approaches c of a constant times a function is just going to be that constant times its limit. So I know in this case that this limit here is going to equal 3 times 2 squared minus 5 times 2 plus 7. And so I'm going to get 3 times 4 minus 10 plus 7, which is going to give me 12 minus 4 plus 9, or plus 7, will give me 9. So in this case, the limit here on this particular problem is 9. Let's look at the second one. The limit as x approaches 4 of the cube root of 2x squared minus 5. Well, one thing I can do with that, I can keep in mind that that particular problem would also be the limit as x approaches 4 of 2x squared minus 5 to the 1/3 power. And so we can plug in 4 on that one. I can take, then our limit properties tell me that that's going to equal 2 times 4 squared minus 5 to the 1/3. So 4 squared is 16 times 2. That's going to be 32 minus 5 to the 1/3 power, which will be 27 to the 1/3, which in this case is equal to 3. So that particular limit is equal to 3. Next one, we have the limit as x approaches 1 of x squared plus 2x over x minus 4. And again, we can, in this case, we can just plug that 1 in. And when we do that, I'm going to get, this will be equal to 1 squared plus 2 times 1 over 1 minus 4, which will be 3 over negative 3, which is negative 1. So in this case, this limit here is negative 1. The last one we have here on this one is limit as x approaches 2 of x minus 2 over x squared plus x minus 6. Well, in that situation, when I do that, I plug that in, I'm going to get 2 minus 2 over 2 squared plus 2 minus 6, which that's going to give me 2 minus 2 over 4 plus 2 minus 6, which gives me 0 over 0. Now you might recall last year when me talking about this. 0 over 0, this is said to be an indeterminate form. And because of that, yes, that is undefined. If you put that 0 divided by 0 in your calculator, it's going to be an undefined statement. But there's other things that happen. And when you get 0 over 0, that means there's some other work you can do that can allow you to determine what that limit is, if it even exists. It's possible that the limit will have a numerical limit. It's also possible that the limit would not exist. That's why it's said to be an indeterminate form. So now let's look at a strategy for finding limits when you have a something that does come out, when you have a function, you want to find it analytically, actually find a numerical value analytically, not using a graph. So the first thing you have to do is learn to recognize which limits can be found by direct substitution. This can happen with polynomials, any polynomial, some of the trig functions that can work, you can do that. The issue you do have with it is, even with vertical asymptotes, that would just mean that the limit does not exist. So you can use those things. And things like e raised to a power, that can also, you can find that by direct substitution. When the limit of f of x cannot be evaluated by direct substitution, where you might have things dealing with fractions, or Or when you do the direct substitution, you get an indeterminate form. You get 0 over 0. Those would be things where we have to go through, and we're going to try to find another function, g of x, which agrees with f at all values of x except at x equals c. Basically what that means is we are going to do algebra. If we're dealing with a function, we're going to try to use algebraic properties to go and rewrite this one in a different way where it would now be able to evaluate it. And to do that, some of the things we're going to use what's called dividing out. And the other one, or we're going to use what's called rationalization. Both of these particular techniques can be used to go and help us identify a limit, to help us find the function g that we're talking about in this that's going to be similar to f. It's going to be the same as f at all values except at x equals c. The first one we want to look at is what's called the dividing out technique. And so in this case, we have a polynomial over a polynomial. And if we go and do the direct substitution on this one, we're going to find that this is actually going to come out to be 0 over 0. So when that happens, what we're going to do is we're going to try to simplify this. And the way we're going to simplify it is by factoring everything and trying to reduce this fraction. Well, I know that this is going to equal, I look at that, x plus 2 I can't factor, but 3x squared plus 5x minus 2 I can. There's a couple things I can do that can help me out with this. So I know this is going to be the limit as x approaches negative 2. In the denominator, we'll still have the x plus 2. But here's the thing we can use to help us out. We know that because of the fact that this did give us, when we did the direct substitution initially, that we would get 0 over 0, that we know there is a common factor between the numerator and denominator. Well, the only factor that can be in this case is x plus 2. And so I know one of those factors is going to be x plus 2. And now I need to identify what the other factor is, what other one we would have. Well, I know the product of the things in this spot and the x has got to be 3x squared, and the only way that's happening is if we had a 3x there, and I know the product of the last two have to be negative 2. Well, that's a plus 2, so it's got to be minus 1. Now you can what you can do is you can pause the video to show that this does factor like this, or you can sit there and say, yes, Mr. Carr, you are correct. So, and with that, we will go on. So what happens now here, the x plus 2 is common, so that drops off. And so this is now equal to the limit as x approaches negative 2 of 3x minus 1. And when I plug negative 2 in, I get negative 7. That is an example of the dividing out technique. The other thing you have with this, you could be dealing with this in with other types of values. You could have, you could see this when you work with a difference quotient, anything like that, or you could even have fractions where you're going to want to do something like that, where you're going to want to get a common denominator. All of that will end up resulting in the dividing out technique. And I can do an example of that in class on Thursday. Now let's look at an example with the rationalizing technique. Now the rationalizing technique is going to end up resulting where you do reduce the fraction and eliminate a common factor. But to do that, you got to get it into that spot first. Now in this case, what we have is the limit as x approaches 0 of the square root of 2 plus x minus the square root of 2 over x. So when I plug in 0, I will get 0 over 0. Which tells me that I need to do some work on this. And what I need to do, I need to be able to reduce this thing. And which means that I need to be able to get, in this case, I need to get the x outside of the square root. And so what we do on this, you might remember, you've got to go and multiply the top and bottom by the conjugate. And in this case, because our square roots are in the top, we're going to multiply top and bottom by the conjugate of the numerator. Now, if you remember, you might remember the conjugate is what you get when you change the sign between the two. So in this case, we're going to multiply top and bottom here by the square root of 2 plus x plus the square root of 2. Or the square root of 2 plus x plus the square root of 2. Now, when I do this particular problem, I'm not going to really multiply anything with the bottom. I'm just going to keep that as it is. But what you really need to also recognize, and it's very important, when you multiply the product of conjugates here, looks a lot like, if you think back to Algebra 1, and we talked again about this at the end of the year last year, this looks a lot like a difference of two squares problem. A minus b times a plus b. Well, when you multiply that out, that was a squared minus b squared. So in this case, what I'm going to get, this is going to equal the limit as x approaches 0 of, when you have that situation in the numerator, it is going to be the square root of 2 plus x, that thing squared, minus the square root of 2 squared, all over x times the square root of 2 plus x plus the square root of 2. And now that is going to equal the limit as x approaches 0. When I square the square roots in the numerator, I'm going to get 2 plus x minus 2 over x times the square root of 2 plus x plus the square root of 2. Now, if I simplify that, combining the like terms, that 2 minus 2 in that there's going to drop off, so that's going to become the limit as x approaches 0 of x over x times the square root of 2 plus x plus the square root of 2. Now, at this point right here, I know that I have a common factor, and I can see that I can now reduce out those x's. And so this is now going to equal the limit as x approaches 0 of 1 over the square root of 2 plus x plus the square root of 2, which equals, in that situation, when you plug 0 in, that's going to be 1 over the square root of 2 plus 0 plus the square root of 2, or that's going to equal 1 over 2 square root of 2. So that would be the limit that I would have for that particular function. The dividing out and the rationalizing technique are going to be two techniques that you're going to be using quite a bit in terms of evaluating limits and working with difference quotients moving forward. And now the last thing we have to do is we got to take a look at what's called the squeeze theorem. Now we're going to look at the squeeze theorem. If, and it's written in green here, if h of x is less than or equal to f of x less than or equal to g of x for all x in an open interval containing c, except possibly at x equals c, and if the limit as x approaches c of h of x equals L, and that's equal to the limit as x approaches c of g of x, then I would say the limit as x approaches c of f of x is going to equal L. So what that means in this problem, we have these three functions, and I know that f of x always is between g of x and h of x. It might be equal to one of them, but it's always going to be between them. And so, and we know that in this case here, because the limit as x approaches c of h of x and g of x are the same value, I know that when x equals c, these h and g are coming together. Okay, they might not be defined there, but they are coming together. And they're going to actually meet at that same spot. So what happens here, since f of x is between them, we can see this diagram up here. Here's g of x in blue. H of x is in the red. And f of x is just some function that's just do right between them all the way through. But what happens is as we move closer and closer to c, since g of x and h of x are getting closer here, we know that f also has to be coming into that point as well. It is always between the two. So therefore, if they both come together at this point, f also has to come together. Again, notice it's not saying anything about what's happening out here with the limits. It's just at the point where the limit of g and h come together. And this is what's called the squeeze theorem, or other people will, sometimes you'll also hear it called the sandwich theorem. Now, this particular theorem is used to go and find a couple of important limits that we will deal with, and we'll go through that in class as well. So this does kind of conclude, it's a quick review of the stuff we did with limits last year. You might want to take a look over your notes from last year as well, if you have them still. And with that, this will conclude this video, and I will see you in class.